that would be bad. So it should be well designed. So real-time systems require minimal times of context switches. So so how do many tasks? Let me see where I am. Okay. So how do many tasks share the same CPU? So okay, so we talked a little bit about round robin, cyclic executive systems, so we're going to talk about it again in preemptive priority systems. And with the latter, well, we'll see what's going on. So first of all, cyclic executive systems, super easy. You call just in a cyclic way all the different threads. So say you have ordered them like this, then you call those threads one after another, and then you repeat, and you go around. So easy to implement. It's used extensively in complex safety critical systems because you kind of know exactly what you're doing. The cons is not efficient in overall usage of the CPU processing. Because maybe, well, with this particular example, I'm not so sure, but say, well, because you know exactly how much time every single one takes, but the point is though that if some of those threads that you are writing may depend on something else that needs to be available from another thread, and if that other thread has not yet been able to make that happen because it's a variable compute time, and you just estimate when that should end, so forth. So then, you may not get efficient use of the overall resources in finishing up the overall system objectives. So also not optimal response time. Say, for example, yeah, what would be a good example here? Well, for example, suppose that I am computing something here, and that is kind of really important. It's like a big alarm or something that needs to be handled right now. But yeah, you cannot because that alarm thread is later on in the sequence and is going to be executing over here. So you don't even have flexibility by saying here, quickly skip all of those and go here. Like, set this one to a very high priority and take that one first by all means, because we're having some dangerous situation. Anyway, so, but this is a very simple system. Round robin systems, several processes execute sequentially to completion, and is often in conjunction with a cyclic executive. And the difference is that each task is assigned a fixed time slice. So I have a fixed time slice, and then I context switch out, and then I context switch in, and so forth. So you have a fixed rate clock that initiates an interrupt at a rate corresponding to the time slice. So in the previous one, you effectively finish this to completion, then you do the navigation work, then you do this, then you do that, then you do this, and then you continue in a in a cyclic executive way. But over here, you just interrupt the task because the time slice is finished, and then you do the next one and the next one, and you go also in a cyclic way, and then you pick up where you have left before, and then you continue. Alright, so preemptive priority systems. So here we say that a higher priority task, so you assign priorities to tasks, a higher priority task can preempt a lower priority task if it interrupts the lower priority task. So priorities are assigned to each interrupt and are based upon the urgency of the task associated with this interrupt. So they can be fixed or dynamic, like you can change the priorities, of course, depending on that. So here we have again these tasks, and they run, and you have different priorities, say, high, medium, and low. And here we have, say, a high priority task in this example, where, oh, I do not know what that word is, a task that, oh, gathers, right. The accelerometer data every 5 milliseconds. Oh, that's very important. Then medium priority, task that collects the gyro data and compensates this data and the accelerometer data every 40 milliseconds, say. A low priority, display the update and do a built-in test or whatever it is. So when this high priority task ought to go ahead, because the 5 milliseconds are done, it interrupts whatever happens. But if there's another task, say task 4 with the same priority, then maybe it has to wait till that other task is finished with its time slice. So say this particular guy over here, the medium priority, say it needs to work now because the 40 milliseconds are over, but it barely starts and this other task comes in because the 5 milliseconds are done, but it's a higher priority, so it kicks out task 2, and which happens here, say, and then starts executing. So what are the problems with multitasking? Well, of course, the advantage is that you now can really assign priorities, which seems to be, which is super important. But a high priority task can, they hog the resources and starve low priority tasks. Because the low priority tasks never have a chance to really start executing if only those high priority tasks are being called all the time. So the low priority tasks share, another problem is, say the low priority tasks share a resource with a high priority task. And the low priority task therefore needs to finish before the high priority task can start. But the low priority task doesn't have a chance to execute, and so the high priority task, even because it has a high priority, cannot actually start executing. So it blocks the high priority task. So how do we deal with that? Well, there are things like rate monotonic systems and priority inheritance. And here we say that the higher execution frequency simply means a higher priority. So that is one approach. And priority inheritance we will talk about right now. So let's explain first of all what's going on here. So let's again take two tasks, one with a high priority, one with a low priority, and say task A is blocked when task C runs. Why? Because they actually share a resource. What does that imply? It effectively assigns the priority of C, which is the low priority, to A, because it has to wait for C. And this is what we call priority inversion. So even though you have high priority, it's sort of inverted to a low priority because of this problem. Task A will be blocked for longer, right? If, say, a task B of medium priority comes along to keep task C from finishing. So task B interrupts task C because it has a medium priority, right? But still lower than A though, which is funny. So it executes, and only after it's finished, task C can continue, finally gets its work done, and now task A can start. So you truly have, like, this problem is even more than you would think. So you really have the task inversion. So a good RTOS would sense this condition and temporarily promotes task C to the high priority of task A. And that's what we call priority inheritance. So the RTOS actually understands this problem and says, you have low priority, but there's a high priority task waiting. So you get high priority now, temporarily. And that's what we call priority inheritance. So on, in this picture, we see that as follows. So priority inversion again, we have task, we have task C going forward. We would like to call task A, but we cannot execute it because C needs to finish. Ouch! B interrupts, B finishes. Finally C is finished, and now the resource is ready for A to use and the high priority kicks in. priority inheritance would be, well, we have C running, A wants to run, cannot run because C has not finished. C gets the high priority of A, finishes, now A can finish, and only after that B, because B has a medium priority. So this is the inheritance, priority inheritance. So that's pretty cool. So, so generally, right, we have a hybrid solution in which we have both interrupt-driven and also non-interrupt-driven processes. The interrupt-driven process we call foreground processes, and the non-interrupt-driven background. It's like it happens at the background all the time at some rate and blah 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 blah. But the interrupt-driven ones may come from your interrupt service routines, or the clock is counted down to 0 and you are ready to do something. That's what we call foreground. So all real-time solutions are just a special case of foreground-background systems. And you will make combinations, you will have combinations. So the Polt loops ID is a background-only system in a way. You're polling the flag. You check for that condition. Interrupt-only systems is what we call foreground-only systems. So the interrupts trigger the interrupt service routine, say, or in your own software you have a certain way of maybe implementing your own way of interrupts, and that triggers the task that you want to execute. Anything not time critical should be in the background, and the background is the process with the lowest priority. So that's the design principle. So so this gives a hybrid system. So we're going to combine what we've seen so far. So we have the Polt loops, interrupt-driven systems. For multitasking we have the preemptive priority, or the round robin, or the cyclic execute, but all of that is going to be a combination. So if we're going back to this example, then what do we see? Well, the Polt loops can be used for the navigation of the sensor task. So we're collecting that data. Interrupt-driven is clearly the clock that drives the scheduler here. The preemptive priority is these different navigation filter tasks, the sensor data processing tasks, and the memory access tasks. So we have those with separate priorities and priority inheritance and so forth wherever needed. So that shows, by the way, that for an application designer you really need to understand real-time operating systems to see to understand how you should set up, how you should tell your real-time operating system how to deal with all your tasks. It's very application dependent, so you need to have a good understanding of how to do this. So the pros of all of this is that it segments the problem into small manageable pieces. So this coincides right with the modular computer system design principle, which is how the software engineer and any other engineer, I think, is working nowadays. This principle was formally written down by, I still remember, well, I do not remember that period, but I remember the paper by Jérôme Salzer, a professor at MIT, as far as I recall, together with a whole bunch of other design principles. So that's why it became sort of that paper that was sort of this really fantastic, beautiful piece that everybody should really have a look at, of many years ago, maybe 30 years ago or even longer. Anyway, it makes more modular software, meaning that you can reuse portions more easily, allows a software designer to prioritize certain tasks over others. The cons are, depending upon implementation, the timing may not be deterministic, as we have said before. It's complex. You do not exactly know when things happen. It becomes more fuzzy. So there's jitter, which is time noise caused by variations in timing of incoming data. The context switching also adds overhead. So we have to live with that. A full-featured RTOS now expands this foreground-background solution. You add network interfaces, device drivers, complex debugging tools, and the most common choice for complex system is to have such a full-featured RTOS, but your robot can live with your very simple own sort of scheduling programmed that you did yourself, but you can also use the free RTOS that we are going to have this assignment about later on. And there are many commercial operating systems available. So how do you choose one? So how do you know which one is right for your application? You have to look at what is driving your system. What's the arrival pattern of interrupts of data? Is it irregular? Is it bursty? Is it bounded with average rate, unbounded, and so forth? What is the critical I/O? Are there absolute hard deadlines? That is crucial, right? Especially for safety critical systems. Wow, you make sure that you meet those hard deadlines. Otherwise, that's a no-go, right? So how do you do that? Later on we will talk about how to do that in, I think, one of the next lectures. But choosing an RTOS approach, so here we have the last two slides. We have this example. How do you know which one is right for your application? So here are some choices. So a reusable launch vehicle for satellites. So the thrust vector control software requires new attitude data every 40 milliseconds, or the rocket becomes unstable. So we choose the cyclic executive. You really got to make that happen on those times. Navigation and control system for submarine, interface to multiple sensors at multiple data rates. Information from the inertial reference unit is most critical, but exact timing of input data is not essential. So you can do some preemptive priority scheme, which would be fine with the highest priority given to the tasks that need those. This is the last slide. So here we have an avionics systems, requires new data from a flight control services. A radar system every 50 milliseconds, cyclic executive, you can do that again. Each task runs to completion, tasks run in series. Last task may not finish before the 50 millisecond interrupt occurs though. Microcontroller running to switch the radar antenna and check for incoming signal. If the signal is there, power up the signal processing chip. So we can choose, say, a pulled loop, and so forth. So that's it. That's the end of this lecture. So it's a lot of material again. Some real teaching of stuff, because this class is so hands-on. But now we'll be able to have a few lectures where we're actually going to talk about some more of this, which hopefully gives you a bunch of extra information to work with. Thanks a lot.